here and you do a shift left, you don't have anything to the left. Let's say you were only dealing with a 4-bit computer, and you do a shift left now, it's an overflow. So then if you shift left on this, you'll get 0, 0, 0, 0, which is 0. So it's not always true that you can just keep doubling numbers. At some point you get a 0, everything's zeroed out because everything's shifted out to the left. So that's why there's this whole concept of overflow, which you'll slowly start getting used to. And a lot of the bugs in software, sometimes some people say the software is buggy, a lot of problems like that can happen. You can have integer overflow in arithmetic, and it's important to kind of understand at the bit level what's actually happening. And we will do some programs like when you do the Java programming, that time I'll tell you how we can test these things. We can print the exact bit representation and see when overflow is happening, when it's not happening, and so on. But that's just to give you an idea. This is not to scare you or anything, but now if you were to have a register on a computer that does multiplication, then you learned multiplication in school, right? Simple, like this kind of thing. Say you want to do 23, 1 into 30, then you do this is all this stuff, right? So you can teach a computer to do it this way too, right? But sometimes you find that using techniques like that increase the speed of your computation, because this requires fewer operations. You don't go through all this. You can just shift a bit to the left and then double a number very quickly. So if you want to just multiply by 2, then you don't have to do the traditional arithmetic. You can use other techniques. So there are some concepts like that. Yeah.
Can you show all the work, how you get the answer?
How you get the answer for which one?
For like the left side, now how do you get the answer for the right side?
Oh, you mean when I shift to the right, you mean?
Yeah.
Instead of shifting to the left?
No.
I didn't get, yeah.
Like show the work, what you just did.
Oh yeah.
Like you said shift to the left, and that's what I see.
I see. So it was not clear when I said shift left what I mean by that, you mean?
Yeah.
Okay. Yeah, sure. So what I mean is, if you have a number, any kind of bit representation, say 0010, okay, and if you want to shift every bit in this number to the left, typically you're not just shifting the ones, you're also shifting the zeros, remember that. So whatever was in this place, this goes out, falls into a trash can. And this goes here, this goes here, this goes here. That's what we actually did. So what I mean is this 0 came here, so we got 0. This 1 came here, so we got 1. This 0 came here, so we got 0. And there was no 0, so we carry over 0. So that's really what we did. So when we shift left, it looks as if we're just moving the 1 to the 0, but we're not really moving the 1 to the 0. We're actually shifting every bit to the left. And it just falls off. So you can think of it as some sort of and it sort of goes in this direction. The last one just falls off. So you actually lose information. Whenever you have, so if you had a 0 here, it's not so much of a problem. Because 0, 1000 is the same as 1000, right? So if you had a 0 before that and the 0 is shift left, then you're not losing information, you're not changing the number. But if you had a 1 here, then a shift left actually damages your number itself, because the 1 is going to go away. So what I meant is, if you had a 1001 and you did a shift left on that, you would end up with a 0010, which is not even double the size. So it's not necessary that when you shift left, you're always going to, if you have an overflow, then you need to know that. So you cannot use a technique to multiply a number by 2 times just because you are right in a few cases. In some cases it's not right. So that's why you have to work harder. So on one hand, this takes longer to compute, but it's accurate. Whereas on computers, when you want to do some shortcut technique that actually speeds your calculation, you got to know what you're doing. You got to know that 1 is in the leftmost position, so shift left is not something you should be doing. So it's just give you an example. Why would it be easy to shift one bit to the left? Because you can think of it this way, as copying a bit from here to here is the cheapest operation a computer can do. Whereas this is a pretty complicated thing, because there are lots of things going on here. You have like, you're multiplying this, so you're multiplying two numbers by three numbers, so it's on average 6 multiplications are what you're doing. Plus you're doing one addition at the end, because you would get something here, you get something here, and then you add up again something, some number here. So you're doing like 6 multiplications and 2 additions. So imagine you're doing that a billion times a second or something. Now, all of a sudden, if you come with some other optimized approach, you would actually save time in doing that. So with computers, you get some of that efficiency, and that's why the computers sometimes give you answers much faster than a traditional calculation. But you can still do it this way, like I said. It just depends how the electronics is implemented. Yeah.
After you move left, what do you do after that? What are you trying to find?
Which one? Here?
What you just did at the bottom. Yeah.
Yeah.
What are you trying to find?
What I'm trying to find? The objective here is simply to realize the benefit of, let's say you had a number like this and you wanted to double its size. One other way you would have done is you would have multiplied 2 by 2 and you would have got 4. But that actually is a longer computation on a computer. Whereas shifting a bit to the left is much easier. So all we are trying to sort of conclude from this is we're trying to come up with a way to speed up the calculation on a computer. If you were to do it the human way, the humans, we kind of do 2 into 2 is equal to 4, right? But on a computer, this might take a little more time than this. This will be much faster if you just move the bit one position to the left. It's a much cheaper operation. So it's not something like a formula or something that you should use. Remember that, hey, I'm going to use this to multiply numbers. I don't suggest. You, in fact, may not even want to use that. Typically, when you're writing programming code, you're just doing x plus y, right? And then, or x into y. You don't really do bit manipulation so often. But in cases where you want to really speed up your program, or you're trying to figure out why some things are running really fast, then it's good to know how somebody else may have used these techniques to improve the performance of the system. So, and it's also that the registers on the computer understand the bits much better than understand these numbers, because everything's stored as zeros and ones. So to convert it back and forth from decimal to binary, binary to decimal is a big overhead in the computer. And that's why just moving a bit to the left, there's no conversion, nothing, just move the bit to the left. It's a very simple operation. It's a dumb operation. But surprisingly, it's equally, a little more fast, I should say, not equally. But does that answer the question?
Wait, so you're trying to do the math, multiplying numbers?
Yeah, so I'm just giving you an example. So I explained to you a little bit about bits and addressable memory. I was just wondering if you are curious why we even do that. What's the advantage of even learning the bitwise arithmetic or the Boolean algebra? So I was just giving you an example that this is one place where this would be useful, is just to know that you can actually multiply numbers just by shifting a bit to the left. But there are lots of other things you could do. So I'm going to teach you things like 1's complement algebra, 2's complement, and there are a lot of ways where you can convert negative numbers into positive numbers, add them up, and then convert them to negative. So there's lots of these advantages you can get on computers that you, once you start learning how the bitwise manipulation works. Some people actually don't use it a whole lot, so, or you may not even like to do it because it's sometimes a little tricky. And when you suddenly start reading a lot of that, tomorrow you start taking a course in computer science, you may feel like, oh, I don't even know how to represent this, or the arithmetic looks really difficult. So I'm just sort of preparing you for that. But over time, I think it will become clearer. Right now, you can just think of this as introduction to understanding how bits are manipulated on computers. But slowly over time, you learn some techniques where you can do a lot of computations on the computer much easily if you just knew how the bits worked. Does that make sense? Yeah, I do have